Hello everybody, welcome to the Ultimate Physics channel. The topic of today's video is at the dawn of modern physics. In this video, I am going to discuss the status of classical mechanics, electromagnetism and thermodynamics at the dawn of modern physics. I am going to briefly review the status of these three major topics in physics, and then I am going to discuss some of the failures of classical physics around the beginning of the 20th century. Before venturing into any study of modern physics, it is important to discuss the status of the physics at the dawn of modern physics and to understand the problems in classical physics that led to the birth of modern physics. Classical physics as it existed around 1890s was largely successful in explaining a wide variety of physical phenomena. Subjects such as mechanics, electromagnetism and thermodynamics had been developed for over 250 years or so, starting from the work of Galileo and Newton to Maxwell, Oyster, Ampere and Boltzmann. Physicists were content with the progress the subject had made and were of the opinion that most of very important laws had been framed and that the essential discoveries had been made, and only what was left to be done was performing better and better experiments to improve the accuracy of measurements with respect to the values in higher decimal places. They could not have imagined that what was about to happen in the following decades could change it all. Let us review some of the essential concepts in mechanics, electromagnetism and thermodynamics. First, let us deal with classical mechanics. The conservation laws in classical mechanics are very important and fundamental in physics. The conservation laws play a significant role in understanding the mechanics of objects. The most essential conservation laws in classical mechanics include conservation of linear momentum, conservation of energy, conservation of angular momentum and conservation of charge. Let us discuss each of these conservation laws in some more detail. So these are the four conservation laws that we are going to discuss in some detail now. First, conservation of linear momentum. In the absence of an external force, linear momentum of an isolated system is conserved. In collision problems, for example, the total linear momentum before collision is equal to the total linear momentum after collision. Let us discuss this in some detail. For example, if m1 and m2 are the masses of two objects and v1 and v2 are the velocities of those two objects before collision, v1 prime and v2 prime are the velocities of the two objects after collision, then the conservation law tells us that m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2. Now, since the equation for momentum P is equal to mv is a vectorial equation, this conservation law holds true in x and y directions as m1 v1 x plus m2 v2 x is equal to m1 v1 prime x plus m2 v2 prime x. This is for the x direction, and similarly one could write an equation for the y axis as well, that is m1 v1 y plus m2 v2 y is equal to m1 v1 y prime plus m2 v2 y prime. This is for the y direction. The next important conservation principle is the conservation of energy, that is, the total energy of an isolated system is conserved in all interactions. This means in collision between particles, the total energy of the particles before collision is equal to the total kinetic energy of the particles after collision. So the equation for energy conservation in a collision problem of two masses m1 and m2 can be written as half m1 v1 squared plus half m2 v2 square is equal to half m1 v1 prime square plus half m2 v2 prime square, where v1 and v2 are the velocities before collision and v1 prime and v2 prime are the velocities after collision. Third conservation law is the conservation of angular momentum. In the absence of an external torque, the total angular momentum of an isolated system of particles around a point is conserved. The equation for that is dl vector over dt is equal to 0. that is the angular momentum does not change with time, where L is the net angular momentum and this L is a vectorial sum of the angular momentum of individual particles in the system. The final conservation law that we are discussing here is the conservation of charge, which is nothing but the total net charge is conserved in all interactions in an isolated system. The 19th century physicists would have included conservation of mass as well to this list, but we know now that mass is not a conserved quantity. These conservation laws, along with the Newton's laws of motion and gravitation, could explain all of the mechanical processes around us. Another important concept in classical mechanics is the velocity addition in problems involving two or more frames of reference. The problem of velocity addition in mechanics follows the Galilean coordinate transformation equations. For example, suppose a spaceship is traveling at a speed of, let us say, 2.5 into 10 power 8 meters per second. Now this velocity, let's say we measure with respect to the ground. So velocity of the spaceship with respect to ground, it is called that as Vt. Now suppose if the spaceship fires a missile, and the velocity of the missile with respect to the spaceship, let us call that Vms, is equal to 2 into 10 power 8 meters per second. Now in this problem, if the direction of the firing of the missile by the spaceship is along the same direction as the spaceship's travel direction, then we can write an equation for the velocity of the missile with respect to the spaceship, right? So velocity of the missile with respect to ground is equal to velocity of the spaceship with respect to ground plus velocity of the missile with respect to the spaceship. This is a simple vectorial equation for addition of velocities, and this follows the Galilean transformation equations. Now if you apply this to this case, we would end up getting the velocity of the missile with respect to ground as equal to 4.5 into 10 power 8 meters per second. This is the result of this vectorial addition, and in this case the direction of the spaceship and the direction of the missile are the same. Hence, the velocity of the missile with respect to ground turns out to be 4.5 into 10 power 8 meters per second, which is larger than the speed of light. So the classical velocity addition equations allow for speeds greater than the speed of light. There is no upper speed limit in classical physics. This turned out to be a problem. We now know that such velocity additions are valid only for low speed situations. Our next topic of discussion is the status of electromagnetism. For over 2 centuries, electricity and magnetism were thought to be separate subjects which are unrelated. Several people such as Coulomb, Oersted, Henry, Ampere, Faraday, etc. had contributed to its development. Maxwell studied the work of these scientists and was able to consolidate the entire body of work into 4 equations bearing his name, the Maxwell's equations in electromagnetism. Maxwell discovered that light is an electromagnetic wave and it does not require any material medium for propagation. Maxwell discovered that light is an electromagnetic wave and all electromagnetic waves travel with the same velocity. He also predicted the existence of other invisible radiation in the electromagnetic spectrum, which was experimentally verified later by Heinrich Hertz. Thus, Maxwell unified the 3 separate subjects, namely electricity, magnetism and optics, into one. What appears as electric field in one frame of reference appears as magnetic field in another frame of reference. These 2 fields are seen as 2 aspects of the same thing. The beauty, elegance and simplicity of Maxwell's equations kept scientists in awe and wonder. But what kept them curious was the unchanging nature of these Maxwell's equations in different frames of reference. Laws of physics are same in all the initial frames of reference, but the mathematical form of these laws of physics could change from one frame of reference to the other frame of reference. For Maxwell's equations, they were of the same form in all the frames of reference. Lorentz discovered that this was not so if Galilean transformation equations were used. Rather, it required a new set of transformation equations named after Lorentz, and it's called Lorentz transformation equations. Now, this was thought to be a problem with Maxwell's equations, and that led to questioning the very nature of space and time. Einstein's special relativity was born out as an answer to these perplexing questions in electromagnetism and questions about space and time. The Newtonian concept of space and time was quite different from our current understanding of these two concepts. Space was thought to be infinite and unchanging for different observers. Any measurements carried out by different observers in different frames of reference must yield the same results. Similarly, time was thought to be absolute. It was thought that time measurements made by different observers in initial frames must be the same. All that was about to change. The fundamental understanding of concepts of space and time were in for a drastic change in the following years. Finally, we will review the status of thermodynamics around the end of the 19th century. Thermodynamics as a subject had been developed for over 200 years due to the work of several people. Using a small number of physical quantities such as heat, temperature, pressure, volume, and internal energy, the behavior of a wide variety of thermodynamic systems could be understood. Steam engines and automobiles have been developed and they were successfully built, and the subject was thought to be ripe. The two laws of thermodynamics, namely the first law and the second law, helped build steam engines and automobiles. Two other laws, namely the zeroth law and third law, helped us understand the concept of absolute temperature and the thermal equilibrium. Now, kinetic theory was successful in connecting the macroscopic thermodynamic properties with the microscopic nature of matter. The atomic nature of matter was still under debate, but the existence of molecules were somewhat confirmed, and the kinetic theory was further developed based on this idea. Now, the ideal gas equation PV is equal to nRT and the equipartition theorem were useful in successfully connecting several properties of ideal gases such as temperature, pressure, and internal energy, etc. Now, the problems in thermodynamics arose from the heat capacity measurement of gases. The kinetic theory of gases predicted the heat capacity of monatomic gases correctly, whereas it failed for diatomic gases and polyatomic gases. Particularly, the heat capacity values at low temperatures deviated significantly from the predicted values for polyatomic gases. And this was a problem with the kinetic theory of matter. Now, Maxwell had discovered a distribution function for the velocities of molecules in gases and thereby distribution of their energies as well. This was further developed by Boltzmann, and hence the distribution function bears their name. The Maxwell distribution function is written as a distribution function which is a function of velocity is equal to 4 pi times the number of molecules present in the system multiplied by the mass of individual molecules over 2 pi kt, where k is the Boltzmann constant and T is the temperature, over 3 by 2 times the square of the velocity multiplied by exponential function minus mv squared over 2 kt. And this is the Maxwell's distribution function. This distribution function turned out to be valid only for certain systems under specific conditions, say in macroscopic systems. In the microscopic domain, nature obeys either of the two other quantum distribution functions bearing the names of Fermi, Dirac, Bose, and Einstein. Few other important discoveries that were made in classical era, and they required a new way of understanding nature. I shall just mention those here. The first one is the discovery of X-ray by Röntgen, and then the next one is the accidental discovery of radioactivity by Henry Becquerel, and then the discovery of electron and measurement of its charge to mass ratio, E by M ratio by J.J. Thomson, and then the observation of spectral splitting and the discovery of what is called as the Zeeman effect. Apart from what has been discussed, there were a few unresolved questions and failures in classical physics. It is worthwhile to ponder over some of these important failures of classical physics leading to the birth of modern physics. The first one pertains to the electromagnetic medium. The mere thought of electromagnetic waves not requiring a material medium for propagation perplexed most of the physicists of the day. All the waves known hitherto required a material medium. Be it waves in water or the sound waves or the mechanical waves, all these waves travel in a medium. To accept that electromagnetic waves could travel without a medium is beyond their imagination. The idea of ether was strengthened and experiments were performed to detect the ether medium. The failure of these experiments was thought to be a failure of classical physics. And the next point pertains to the electric and magnetic fields and their measurements. The varying nature of electric and magnetic fields as measured by moving observers could not be explained using classical ideas of space and time. The unchanging nature of Maxwell's equations in different frames of reference and the requirement of a new set of transformation equations to understand this was considered unclassical. The third issue pertains to the black body spectrum. The black body radiation is another important problem that keeps physicists engaged at the dawn of modern physics. A black body is basically an object that absorbs all radiation incident on it. It can be thought of as a cavity with a small hole through which it absorbs all radiation. The black body also ought to emit radiation across all frequencies, so not only it is a very good absorber, it is also a perfect emitter. Now the resulting spectrum between the emissivity and the frequencies has a peculiar shape which could not be explained using classical ideas of thermodynamics or mechanics. Several laws were proposed and none of them could explain the black body spectrum over the entire range of spectrum. This was a failure of classical physics. Now finally, on the observation of emission of electrons from the surface of certain metals when light is incident on the surface. This observation was called as the photoelectric effect and it could not be explained classically. Now the dependence of the emission of electrons on the frequency of the incident radiation rather than the intensity of the radiation as one would expect classically could not be explained. This was another failure of classical physics. These failures led to the birth of modern physics. At the dawn of modern physics, two important theories were proposed, namely the Special Theory of Relativity and the Quantum Theory of Matter and Radiation. Most of the developments in physics over the last 125 years is due to these two theories. It would not be an exaggeration if I say that it has been keeping physicists busy to this day. We have already covered the first of these two theories in some detail in some of the previous videos in this channel. And that brings us to the conclusion of this video. Hope to catch up with you soon on another interesting video. See you then. Bye bye.